Hello everyone, my topic is source-to-source CUDA to SYCL code migration tool, Intel DPC++ compatibility tool, and open source SYCL project. I am Wang Ziming, senior software engineer from Intel. Here's today's agenda. First, I will introduce why do we need a code migration tool. What is Intel DPC++ compatibility tool and open source SYCL project? Then I will introduce the usage flow of the SYCL and the architecture of SYCL. After that, I will present a migration example, a migration rule example, and a user-defined migration rule example. At last, I will finish the presentation with summary and call to action. While hardware innovation has led to a diverse, heterogeneous architecture landscape for computing, software development has become increasingly complex and difficult to take full advantage of CPUs and accelerators. Developers are looking for open alternatives that add time to value, and Intel is providing an easy, short pathway to competitive hardware choice. SYCL is an open alternative to single architecture property programming technologies. SYCL extends C++ capability in the way that C++ was intended to be extended to offer multi-architecture support and disjoint memory configurations. Intel employs open development to advance ecosystem innovation, and CUDA to SYCL code migration tool provides developers a productive path to create single-source portable code. So, what is Intel DPC++ compatibility tool? The tool assists in migrating your existing CUDA code to SYCL code, which can run on any platform that has SYCL compiler support. Intel One API product provides a cross-architecture compiler, DataPalo C++ compiler to support C++ and SYCL. Also, Intel One API product provides advanced libraries and a set of tools for developing high-performance, data-centric applications across diverse architectures. Intel One API product support both direct programming with SYCL and API-based programming. The tool ports both CUDA language kernel and library API calls. For CUDA kernel, the tool ports to SYCL kernel. For library API call, the tool ports to library API call available in One API product. Tools was developed by analyzing declaratory code of CUDA and developing migration rules that allow porting of CUDA code to SYCL. The goal of the tool is to make it as easy as possible for developers to migrate their existing CUDA code to SYCL code, improve code migration efficiency. The Intel DPC++ compatibility tool is included in Intel One API-based toolkit. What is open source project SYCL? To enable the ecosystem, including cross-architecture code, Intel open-sourced technical components of its DPC++ compatibility tool to create project SYCL. Project SYCL is a source-to-source code migration tool that allows developers to create single-source portable code for hardware targets regardless of vendor. By reusing code across architectures, this simplifies development while delivering performance and productivity, and reduces time and costs for ongoing code maintenance. Along with the code migration tool elements, Project SYCL is a community for developers to share, collaborate, provide feedback, and contribute software technologies to further open heterogeneous development across CPUs, GPUs, and FPGAs. SYCL will be available on GitHub in coming weeks. Welcome to use the tool and provide feedback. Really good news, Intel is going to open source SYCL. In following pages, I will focus on SYCL. This page presents the usage flow of SYCL. The picture shows the usage flow of SYCL. Given a CUDA source, it is migrated to the SYCL code finally. In the usage flow, SYCL first tries to collect compilation knowledge of developers' CUDA source from project code build scripts. Then, with compilation knowledge of the CUDA source project, SYCL assists developers migrating code written in CUDA to SYCL by generating SYCL code whenever possible. Typically, about 90% of CUDA code can be migrated to SYCL code automatically. For CUDA code that SYCL can't migrate automatically, inline comments are provided to help developers to complete and tune the code. After developer finish the coding, developer need to verify the code, make sure it is correct. Based on the correct code, developer can further tune the code to desired performance and run on any SYCL-capable hardware. This page presents architecture of SYCL. SYCL mainly contains three function components: intercept build, the DPCT binary, and help head library. The intercept build is used to collect compilation options of the CUDA project by intercepting build process of CUDA project. During source-to-source migration, those compilation options are used to identify the active code path, head files dependencies when build AST tree for CUDA code. The DPCT binary. It is the main component of SYCL. It does source-to-source migration based on compiler front-end technology. Here list the main build blocks for DPCT binary. Clean CUDA front-end. It passes CUDA code into AST tree. AST analyzer. It analyzes the AST, build out inter-procedure information, including define and use information of variables, function call, graph, cross-file dependencies, and so on. Migration rule engine. It is the core build block of DPCT binary. It implements a set of migration rules. Each migration rule is designed to migrate a CUDA syntax. With more migration rules, the DPCT can migrate more code, syntax, and scenarios. When migration rules are scheduled to run, it finally generates a set of source modifications. The load engine. It does cleanup of duplicated source modifications, solves the conflict among source modifications, and applies the final source modifications to original CUDA code to generate SYCL code. Claim format. Target format the migrated code. Make migrated code more easier to read. Help head library. It provides help functions to assist the migration of CUDA code. These head files written in C, C++, and SYCL are intended to become part of migrated code generated by SYCL-O-Matic. Developer can copy these head files if needed and include them in the generated code. This page presents more detail of help head library. The help head library is pure head file library. The help use interface includes memory API, device API, image API, atomic API, math API, and some libraries API. And those API are wrappers of corresponding SYCL class and one API library APIs. All the help functions are implemented in DPCT namespace. This page and the next page presents migration example vector add. Sample code vector add implements a vector add function with kernel. In the page, the left side is CUDA code and the right side is SYCL code migrated by SYCL-O-Matic. The highlight blocks shows difference between CUDA code and SYCL code. For code block 1, its head file includes statement migration. In CUDA code, CUDA.h is CUDA head file. In SYCL code, SYCL.hpp is SYCL runtime head file. And dpct.hpp is help head library of SYCL-O-Matic. For code block 2, it is kernel function migration. In CUDA code, keyword global is used to define a kernel function. In kernel function body, CUDA's built-in variable thread IDX, which returns thread ID for current thread in a thread block, is used to index data array. In SYCL code, there's no keyword global. Vector add kernel function is a SYCL device function. Class SYCL and the item has equivalent function to return thread ID for current thread in a work group. So in SYCL code, actual parameters SYCL and the item is inserted in function. For code block 3, it's about memory allocation migration. In CUDA code, it uses CUDA malloc runtime API to malloc device memory. CUDA malloc API only requires a point and a size. Note here, CUDA runtime will do some initialization work implicitly, like select CUDA device, set up device context, and so on. In SYCL code, the device memory allocation function is SYCL malloc device, and the SYCL malloc device function requires an actual parameter SYCLq. So the SYCL-O-Matic generates actual code to get SYCL device and get SYCLq associated with SYCL device. Consider the SYCL device and SYCLq will be used more than once. SYCL-O-Matic introduces actual local variables to make the code more readable and less verbose. For code block 4, it is kernel code migration. In CUDA code, CUDA uses the special syntax 3 pairs of angle brackets to submit the kernel to run on the GPU device. In SYCL, it uses submit method of SYCLq to submit a kernel specified in PAL4 to run on device. In this example, in PAL4, it defines a lambda kernel function which calls the vector_add device function. In CUDA code, the configuration of CUDA kernel work/threads is specified by grid and block in the 3 pairs of angle brackets. In SYCL code, in PAL4 function, it uses SYCL range to define the work/threads for the SYCL kernel. For code block 5, it is migration of memory copy. In CUDA code, it uses CUDA memory copy API. It is a synchronous API. In SYCL code, it uses memory copy method of SYCLq class, and it is asynchronous, so it is further calls wait method to make sure copy finish when the call return. For code block 6, it is migration of memory release. In CUDA code, it calls CUDA free API to release device memory. In SYCL code, the memory free function is SYCL free. The only difference here is SYCL free requires SYCLq as actual parameter. For code block 7, it is pure C or C++ code. They are same on both sides, so just keep unchanged. This page gives an example to show how to write a migration rule. Migration rule is core magic in SYCL to do source-to-source migration. Here give an example on how to implement a migration rule. First, figure out the equivalent functionality in SYCL. For CUDA malloc API in the sample code, its equivalent in SYCL is SYCL malloc device API. Then, in given AST tree, try to find out CUDA malloc node. One method here is to define an AST matcher to visit the AST tree to match the call expression node which has callee as function declared CUDA malloc. After got CUDA malloc node in AST tree, it can further visit the call expression node, analyze the parameters of the CUDA malloc function, and generate equivalent code in SYCL. Each migration rule can be implemented to migrate a simple language syntax. With more migration rules added, the SYCL will be more powerful. This page presents a migration rule feature, user-defined migration rule. With user-defined migration rule, SYCL can extend the migration capability by defining migration rules in YAML file. For example, rule first in line here is a micro-migration rule. It is defined in YAML. It can be loaded by the SYCL. The rule guides the SYCL to migrate micro first in line to micro inline. User-defined migration rule has target to cover more syntax, like migration of API, data type, class, and so on. Part of the feature will be available in next Intel 1 API release. Summary and call to action. Both Intel DPC++ Compatibility Tool and SYCL assist in migrating your existing CUDA code to SYCL code, which can run on any hardware that has SYCL compiler support. Intel DPC++ Compatibility Tool is the Intel product version of SYCL. SYCL will open source in the coming weeks. Just give a try on Intel DPC++ Compatibility Tool and SYCL. SYCL will be available in GitHub in the coming weeks. Send us feedback. That's all. Thank you.